The last time I touched this project, I was working on terrain systems, but I kept getting held up trying to fake that the terrain was spherical in order to have seamless travel from space to planet. I tried to use a shader to bend the terrain under the horizon the further it was away from the player, but all that led to was objects floating above the horizon because they didn't share the same shader code. I tried syncing the skies between space and the planet's surface, but it led to issues with speed as things approached the flat world. I tried wrapping the planet on the X and Y axis without properly thinking, which actually made the North and South poles the same place, because wrapping the X and Y axis turns your planet into a donut and not a sphere. My solution to this was to just put walls up to prevent the player from going to the planet's poles. But what happens when the player decides to just try and land on the poles from space? How do I handle that scenario? All in all these tricks and illusions are taking up more time to implement than just actually having spherical worlds. So I think it's time to stop trying to make planets great again and just implement spherical worlds. We can treat the planet like 6 flat terrains. Each one faces outwards, forming the 6 sides of a cube, and as we subdivide each face, we normalize the vertices around the center to create our spherical terrains with a decently consistent resolution. We can improve the distribution of points a little bit more by using this funky little formula that I stole from cat-like coding to even out the points that were congregating at the corners of the cube sphere. Now that we have some points, we need some triangles. I've put together this editor window to make life a little easier. We're going to treat each of these points as a terrain chunk that is roughly 256 meters by 256 meters with a 1:1 resolution. Generating each mesh is as simple as generating a flat terrain chunk, except we normalize each vertice around the sphere. Now that that's implemented, we have some white balls. However, it would appear that this is not as easy as I thought, as my white balls are inside out. I forgot that different 3D programs have different coordinate systems, and it appears I got my left and right mixed up. I just fiddled with the indexes until I got it right, but now I have another problem, which is these ugly seams that have appeared. Turns out I got the position of each vertice slightly wrong. I was calculating each vertice's position, assuming each chunk was 256 meters. But this is not correct. Each chunk has 256 points, and at a 1 meter resolution per quad, that means each chunk is actually only 255 meters. This error led to 1 meter gaps between each chunk on the positive X and Y axis. Anyway, now we finally have something that we could call a planet. But now we have a new problem, and that's performance. Premature optimization is the root of all evil, but in this case I think it's warranted, as currently a very small planet with a surface area of only 5 square kilometers is running at 43 frames per second while doing nothing. Right now, our planets are made up of 6 terrain faces, which contain our chunks, which are each an individual actor with a child actor mesh and a child actor collider. This is all overkill, and it's time to get rid of all this overhead. Terrain faces were a useful idea while learning, but they are not necessary, and all the chunks can sit in one array. Chunks also don't need to be actors with child actors. Having all these actors in the scene makes our scene size balloon to the point where I can't even check it into GitHub, and a chunk can just be a struct holding the chunk's specific data. Lastly, we need a level of detail system. If the player were to fly out of the atmosphere and look back at the planet, roughly half of the planet's chunks would be visible at one time at a 1 meter resolution. At this distance, there is no point showing the terrain at such a high resolution to the player. The player is so far away that each triangle is smaller than a pixel, and subpixel triangles are very bad for performance. After gutting the codebase, we now have one actor in the scene holding all of the chunk data. While I was doing that, I had a little play around with this mesh culling system that uses the angle of the chunk from the camera to determine whether or not it is in view. The only problem is that it fails to cull chunks that are blocked by other chunks once the camera gets too close to the planet. But that's okay, because I think I found a better way to do this. By calculating the distance to the horizon from the camera using this old thing, and then checking each chunk to see if it is within that distance. Even better, while we're looping over the chunks, we can use the distance to each chunk to calculate the level of detail we want the chunk rendered at. To get this to work, I had to move the chunk mesh generation code out of the planet editor and into the chunk struct, which I think makes more sense anyway. I made some changes to it so that it accepts an integer representing the level of detail we want, and then using a little bit of math, it determines the number of points for the mesh. While I was knee deep in it, I had a go at multi-threading the mesh generation, and that went great, as you can see. The mesh generation is already pretty fast, running on one single background thread, so I think I'll come back to this and try it again later. For now, I'm going to move on and give these planets a more interesting surface. Right now, the planet is just sampling 7 octaves of simplex noise, but the lighting is a little funny. This is because I forgot that normals are a thing. Right now, the terrain normals all face outwards as if it were a sphere, failing to account for our terrain's new bumps and valleys. To fix our normals, we need to account for the terrain formation by sampling the noise function 2 more times and subtracting our first point from the new ones. Then using the cross product as our normal vector, this should fix our problem. This did not fix our problem, and now it looks kinda crunchy, and I'm not sure why. I found out why. It's because I forgot to normalize my normal vector, and now our terrain is shaded properly. Okay, so the keen-eyed among you may have noticed that I swapped game engines for a bit. During the whole Unity runtime debacle, I learned Godot, Flax, and GameMaker. Flax's API is very similar to Unity's, and they both use C#. As a result, the planet system works in both with minor tweaks to class names and functions. That being said, now that we are back in Unity land, I want to spend a little bit of time moving the planet mesh system from C# tasks to Unity's own job system. The main benefit of jobs is that they're supposed to be faster. That being said, they are not made for large, long-running processes. Roughly, max duration should be like 4 frames. So instead of one long background process, I have split it up into smaller jobs so that the Unity gods don't smite me. The first job loops over all the chunks in parallel and works out which ones are visible to a camera and what level of detail it needs to be generated at. The second job loops over each chunk that's visible and generates the vertices, triangles, and normals in parallel. The third sets it all up in one big single mesh, and this works well enough. A lot of this could be moved to the GPU in the future. The only reason I made this so CPU-sided was because servers don't have GPUs, and I needed a way to generate terrain on the server. And who knows, maybe this way will work better for people with integrated graphics. Anyway, I really want to work on visuals right now. I want to try make my own render feature that gives this planet a nice atmosphere, but there are more pressing things to work on, so that's it for now. See you in the next one. Ciao.